Good morning, sir.
Okay, so in the last class we started our discussion of differential length. Okay, and I'm sorry that I have not prepared the slide. So actually I'm using Professor Ram's slide for this presentation, and I'll discuss that how this differential length in one coordinate system. So let me share it. Yeah, so this differential length in one coordinate system can be converted into another coordinate system. So you can see one of the things is that from the how can I say, so from the geometry itself you can understand that why the differential length definition in every different coordinate system are different. Okay, so that can be explained. Okay, and so I'll discuss it later on. So before that, how this you can say this is basically universal definition. Okay, so the Cartesian coordinate system is the universal definition. Okay, so everything, because we basically understand the Cartesian coordinate so well. Okay, and we can easily imagine that. Okay, so that is the reason that we basically, whatever the definition, whether it's curl, whether it's divergence, whether it's gradient, we basically initially we define in the Cartesian coordinate system, and then later on we can convert into any other coordinate system based on the coordinate transformation. Okay, or basically coordinate transformation matrix. Okay, or basically the rotation matrix. Now see that in the last class I tried to start the discussion, but in that class I was not able to complete that one. That uh, you can see that differential length can be represented as dx in the basically in the x direction plus dy in the y direction plus dz in the z direction. So these are the basically unit vector in different x direction. This is the unit vector in the y direction, and this is the unit vector in the z direction. So this is basically represent the effective differential length. Okay, so if you have increment, in all the directions, so dx means basically a small amount, a very infinitely small amount of increment in the x direction, and dy is basically infinitely small increment in the y direction, and dz is the infinitely small increment in the z direction. Okay, so this differential length in Cartesian coordinate can be converted into the differential length in the cylindrical coordinate by using coordinate transformation method. So how? Okay, so before that, let's write this equation. So let's write this equation in a vector form, or basically with the matrix vector. Okay, not just normal vector, but matrix vector, because one of the things that if you understand the linear algebra properly, then you can solve many problems in a very efficient manner. Okay, because uh, you can understand that basically the computer, any computer system is basically, or whenever the computer system solve any problem, so that basically divide the problem into linear equation. Okay, and those linear equation by basically solve using linear algebraic system. Okay, or basically the matrix system. Okay, so let me share this my screen here. Okay. Okay. So if you understand this analogy, then you can do the other by yourself. Okay. That how, what is going on? Why it is basically represented like this? Okay, for let's say that dl dl, this is the unit vector. So that is basically you have dx and you have x unit vector, then plus dy you have y unit vector, and plus t z, you have z unit vector. Okay, so this is a summation. Now you have seen that any summation can always be represented as a basically vector dot product. Any summation can be always be represented as a vector dot product. Okay, so let's write this as a vector dot product. Let's write this as you have x, which is a vector, comma y, which is a vector, comma z, which is also a vector. Okay, so please note that they are not scalar. Now here you have another vector that basically represents dx, then you have dy, then you have dz. Okay, so this is a vector, and this vector basically the element of this vector is dx, dy, and dz. Okay, so increment in the x direction, increment in the y direction, increment in the z direction, and here x, y, and z. What does it mean? So this basically means, so x is basically in our Cartesian coordinate system, it is 1, 0, 0 vector. Then y is basically 0, 1, 0 vector, and z is 0, 0, 1 vector. Okay. Now what we'll do, we'll write this dx, dy in terms of basically using the variable transform. Okay, so using the variable transform, we'll write this in terms of rho, phi, and z. Okay, so let's write that x is equals to rho cos phi. Now dx you can write is d rho cos phi minus rho sin phi d phi. Okay. Now similarly we can write dy. So dy is basically y is equals to rho sin x. Okay, rho sin phi. Okay, so rho sin phi means basically you can write is as d rho sin phi minus rho, sorry, not minus, it should be plus, rho cos phi. So basically sin phi derivative is cos phi d phi. Okay, and del z is del z. dz is equals to dz. Okay, so write it here in a matrix form. So you can write this in a matrix form. D rho, d phi, and d p. So what should be my first row?
Sir, it should be cos phi,
then
0, 0.
minus rho sin phi, and then 0. Okay, then here you have sin phi, then rho cos phi, and then 0. Okay, and the last is 0, 0, 1. Okay, so if you multiply this vector with 0, 0, 1, you will get del z. If you multiply this vector with sin phi, rho cos phi 0, then you will get rho del d rho sin phi rho cos phi into d phi. Similarly, if you multiply this column vector with this row, then you will get this value. Okay. Okay, so now to convert this into cylindrical system. Okay, so this is in Cartesian system. So convert this into cylindrical system. What you will do? We'll use the property that this x can be written as rho vector into phi vector So these are, please note that these are basically unit vector, row vector, phi vector, and z vector in the cylindrical system. These are basically unit vector, not the coefficient. Okay, please note that. Please note that these are basically the unit vector. Okay. Now this is identity matrix. So we have to multiply this with something that get identity matrix. So what should I multiply with this? So what is the property of this matrix? So this is a matrix, no? So what is the property? How can I get that identity matrix? What should I multiply with this?
Inverse of that rotation matrix.
Inverse of this one. Now the beauty of this, the inverse of this is basically transpose of this, because it is an orthogonal matrix. The inverse of this is basically the transpose of this. Let's multiply the transpose. So basically you need to multiply this one. Row vector transpose. So basically just I am writing in this manner. Then you have phi vector transpose and then z vector . Then you have phi, then you have z. Okay. Okay, now what is row vector transpose? So let's write the row vector transpose. Row vector is cos phi, sin phi, 0. So therefore you need to write that cos phi. So cos phi, sin phi, 0. That phi vector transpose is basically this one, minus sin phi, sin phi, cos phi, 0. And z vector transpose is basically 0, 0, 1. Okay. Now you have this matrix, that is cos phi minus rho sin phi, then 0. Then you have this thing, sin phi, rho cos phi, 0, then 0, 0, 1. Now this into, you have at the end you have the differential operator, the differential vector d rho d phi, and then okay. So if you do this multiplication, what will happen? So in this row, if I multiply this row, this column with this row, so what is the product?
1.
Okay, so if I write this, so let me write this. You have row vector, you have phi vector, you have z vector. Okay. Now if you multiply this, you will get 1. And then if you multiply this column with this row, what will happen?
0.
0. It will 0, and then last one also 0, because it is 0, 0 and 0. Okay. And similarly, this will be 0, this will be rho, this will be 0, and then you'll get this basically will get 0, this will also 0, this will be 1. Okay, and then you have this differential operator, the d rho, d phi and dz. Okay, so I'm removing this part. So at the end, what it look like? So you have rho unit vector, then you have phi unit vector, then you have z unit vector. Okay, and the differential operator, if I multiply this, so basically everything will be scale. So you have d rho, you have d rho, then you have rho d phi, then you have dz. Now, if I multiply this, then what is the final result? So that is basically you have d rho in the direction rho, then you have plus rho d phi in the phi direction. Okay, then you have dz in the z direction. Okay, so this is the definition of differential length in a cylindrical system. Okay, so you can understand how to derive this one. Okay, so how this is basically the universal definition is basically in the Cartesian coordinate system. The universal definition or differential area or differential volume is basically in the Cartesian coordinate system, but we can easily convert this into another system. Okay, so this is the actually main you can say the way you can convert this one into another one. Okay, so in this way you can do from cylindrical to let's say spherical also. Okay, and then from you can say Cartesian to spherical also you can do that. Okay, so this is the basic way to do this kind of operation. Okay, let me share this one and share from this one. Okay, so you can understand that how this equation or basically this differential length can be obtained from this differential length. Similarly, the differential area. Okay, so the differential area del S of a you can say in Cartesian coordinate system can be obtained. In a Cartesian system can be converted into cylindrical system also. Okay, so you have to use the same analogy, and using that you can do that. So it is not a big deal. Okay, and similarly you can do the same thing for the differential volume also. Okay, now what is differential area? So we have not discussed about the differential area. So what does it mean, the differential area? Okay, so it is basically the incremental area in a particular direction. So how area can have a direction? So the direction of the area is nothing but the normal to the surface. So here this is an example. Yes. Yes. Shubhangshu, Chandra, do you have any question? Hello. Hello, do you have any question? Shubhangshu?
Sir, I think it's done on by mistake.
Okay. Okay. So what does it mean by the differential area? Okay, or basically the differential surface. So the differential surface, for example, in the x direction, the differential surface is basically dy and dz. Okay, so the increment in the y direction and increment in the z direction and product of that. Okay, so increment in the y direction, increment in the z direction, and the product of that, and the direction of the surface is basically normal to the surface. Okay, so this is basically normal to the surface. Okay, and similarly, you may have the differential area in the y direction, and if you combine these two, then you will get the total differential area. Okay, so the resultant direction obviously it should be in the middle. Okay, it is basically in the diagonal of this surface. Okay, so the resultant direction is basically diagonal on this surface. Okay, so the surface is basically you can say that is basically diagonal of this surface xy. Okay, so the resultant direction of this differential area is basically the diagonal in the xy surface. And similarly, you can have that if I add all the three differential area, then you have the resultant direction of the area will be something that is basically diagonal of the cube. Okay, so this is basically the resultant direction of the differential surface is basically the diagonal of the cube. And in this way, why we represent in this way? So when we basically let's say I need to find out, let's say certain volume. Okay, so certain volume, then it is basically differential length into differential surface. So if I want to find out certain volume, so it is basically differential length into you can say the differential surface. So in that way we can sometimes able to find out the volume. Okay, and also let's say you have a certain surface integral. Okay, so you have a vector and vector having a certain surface integral. So in that case, the ds it is very helpful. Or for example, if you have certain line integral, so in that case differential length is very helpful. Or if you have certain volume integral. So let's see what is differential volume. Okay. So the same thing has been represented in a differential in a different system. So let's see what is differential volume. Yeah, so this is basically differential volume. Please note that the differential volume is basically unitless. Okay, so sorry, basically directionless. The differential volume is basically directionless. It does not have any direction. Okay, so the differential volume is a direction or basically scalar quantity, but differential length can be a vector quantity, or differential surface can be a vector quantity. Okay, and this is very useful when you do, let's say, volume integral. Let's say you want to do that certain, let's say you have a volume charge distribution. Okay, so let's say you have a volume charge distribution over a particular volume. Let's say you have a rectangular area, or you have a spherical area, spherical volume, or you may have let's say how can I say, spherical, or you may have a cylindrical volume. Okay, so inside the cylindrical volume, that I want to find out the, let's say, total charge. Okay, so you have a charge density is given. Okay, so the volume charge density is given, and I'm giving you, please find out that how much is the total charge enclosed inside the volume. Okay, so for example, if you have a cube, then it is easy to use the Cartesian system. Let's say you have a sphere. Let's say you have a sphere, then it is easy to use the spherical coordinate system. Or if you have a cylinder, inside the cylinder, how much is the total charge? So in that case, it is easy to find out using the cylindrical coordinate system. So that's why we use different coordinate system to find out or to solve a particular problem. Now think that, let's say let's consider that the volume we are considering, that is not in regular shape, that is in irregular shape. So how we can solve this? Let's consider you have a certain charge distribution over a irregular volume. Okay, so it is not a regular geometry. Regular geometry means not, it is neither a cube nor a you can say sphere, or not a cylinder. So in that case, how do you proceed? How to solve that kind of problem?
Taking very small cubes.
Yes. Okay. So basically, we'll divide the volume into small volume. Okay. So we'll divide the volume into small volume, and we can divide the problem into small problem. Okay. So basically, the large problem can be divided into small problem, and then we'll solve that small problem, and then at the end we can add all the result clap together. Okay. So in that way we can solve that how much is the, let's say for example here if you have a volume charge density and you want to find out the total charge inside that particular volume, and then we can proceed in that way. Okay. Okay, so this is done. Then okay, and then another thing I would like to mention that from the geometrical concept also we can understand that why that differential length in Cartesian coordinate system and differential length in the cylindrical system are related. Okay, so let's see that from the geometry itself how we can understand. So okay, so this geometry is fine. Now you can see that this in this direction rho basically represent a distance. Rho basically represent a distance, and d rho is basically an incremental distance. Okay, but phi represent angle. Phi is not a distance. Phi represent angle. Phi is not a distance. So you have seen that one of the formula for triangle, that is basically the base. If the angle that if you have a I can say bilateral triangle, if you have a bilateral triangle and you have that length, sorry, that angle is very small. Okay, angle is very small. So if we consider this angle is very small. Okay, so that del phi, if del phi is very small, then we can say this length is basically rho into del phi. Rho is the basically height here. Okay, rho is the height, or basically you can say the distance from the origin and the point we are basically measuring. Okay, so distance from the origin and the point we are measuring, and that rho into d phi is the incremental length. D phi is not an incremental length, it is an incremental angle. Please note that d phi is an incremental angle. Okay, so it is an incremental angle, and rho d phi is incremental length. Okay, so that's why in the phi direction you have rho into d phi. Okay, so this is the, you can say that this is a kind of how can I say, this is basically geometric proof. Okay, so basically geometric idea that why it is rho into d phi instead of only simple d phi. Okay, and simply in the z direction is basically, this is basically represent length. Z itself is a length. Okay, so therefore dz is an incremental length. Okay. Got it? Using the same analogy, we can show that in case of spherical system also, so r is basically length. R is length. So dr is basically incremental length, but theta is basically theta is basically angle, and d theta is basically incremental angle. So this much is the incremental angle. Okay, so this much from this angle you can understand this one. Okay, so this angle is basically d theta. Okay, and so therefore r into d theta is basically, so this one r into d theta is basically this much incremental length. Okay, so r is the distance from the origin, and d theta is change in angle. Because d theta is very negligibly small, so we can consider this length as r into d theta. Okay, and similarly that in the phi direction, this r sine theta is the basically the you can say if I consider that in the xy plane. So if I consider that only in the xy plane, the length of the vector is basically r sine theta. Okay, r sine theta into d phi is the incremental distance in the phi direction. This is the incremental distance in the phi direction. Okay. Okay, so this thing done, and in the same way analogy we can explain the surface area also, or also the volume. Okay, that how this basically has been formed. Okay, and another way we can prove that in a mathematical way, that how that coordinate transform are going on. Okay. Okay, so this is fine. Now we'll move to the next thing, that is basically vector field. This is done. So before moving to vector field, so you need to understand some certain type of integration. Okay, so so there are actually three type of integrations are available. So one is basically line integral. So you need to do, let's say you have certain vector quantity, so which is varying over the, you can say over this field. Okay, so you have a vector quantity which is varying over this field, and you want to find out that let's say for example, yeah, the field is basically electric field. Okay, the field is basically an electric field, and one charge is there, and you want to move that charge from this point to this point and follow this line. You want to move the charge from this point to this point and follow the line. So for that, how much is the work done you have to do? So for that, you need to do one line integral. Okay, so for that you need to do, so basically force into dl, you have to do the integration over this line length. Okay, so over this line L, you have to do this integration from this point to this point. Okay, so this is a open integral, and there are cases that in some time you have to do a closed path integral. Okay, so this is the symbol of closed path integral. Okay, and you can understand this line is basically in general in most of the cases is a vector quantity. Okay, in most of the cases, so it is the incremental length dl. Okay, and similarly, let's say you have to find out, for example, how can I say? So let's say you have to find out the total flux. So you know the magnetic flux density B. Hello.
Yes, sir.
Yeah, so basically, let's say I want to find out that how much is the total flux crossing a particular surface. Okay, so for that, what you have to do? You have to find out the surface integral. If I want to find out the total flux, so flux density is B. So if I want to find out the total flux, then I have to do a surface integral over that particular surface. Okay, this is the surface area, and you have to do the surface integral. And then you have the volume integral. Okay, so volume integral, let's say you have a volume charge density. Over a particular volume, you have a volume charge density. Then you are trying to find out how much is the total charge there inside that volume. So for that, you need to do a volume integration. Okay, and there is another thing that is basically closed surface integral or controlled integral. Okay, so you have a closed surface. So inside the closed surface, you want to find out, let's say you have a certain surface charge density over a closed surface, then how much is the charge enclosed inside the surface. So for that, you can do the closed surface integral. Okay, so this thing is not fine. Now move to field and this thing. Okay, so I have discussed this. this thing I have discussed. Now move to the Dell operators. Okay, so now it comes to field. Okay, so scalar field and vector field. So can you provide some example of scalar field?
Temperature distribution.
Temperature distribution over a room. Other than this,
Charge density.
charge density. Oh, yeah, this is also an example of scalar field. Okay, so a field is basically something which is varying with respect to space. Okay, something which is varying with respect to space. At different spatial point, it has a different value. And in case of vector field, it will not only have certain value, it will also have certain magnitude also. So it is not only having value, but also having certain magnitude. So let's see. So you have a three-dimensional volume. Inside the volume, the magnitude is basically varying. Okay. So you have a three-dimensional volume, and inside that volume, that magnitude. So basically, darker means basically you will have the lightest field strength, and lighter means basically having higher field strength. Okay, so that darker area means you have low field strength. The field strength is low, and whiter area is basically higher field strength. Okay, and here it is the vector representation of the field. Okay, so it is you have a vector field F, and here the arrow magnitude, the arrow length is basically indicate the magnitude or the field strength. So where you have a more arrow magnitude means you have a more field strength. Okay, and where the magnitude of the arrow is small, we have less field strength. For example, this area, here you have a field strength is low, and this area you have a field strength low, and in this area you have a field strength low, and here this area you have a higher field strength. Okay, and the direction of the arrow basically indicate that in which direction this vector field are oriented. So please note that over the surface area, over the surface at different point, it has a different direction. Now, for example, you have seen that if you have a charge, so if you have a charge, the electric field created due to the charge is basically always pointing outwards from the, let's say you have a positive charge, and the direction of the electric field is basically pointing outwards from the charge. Okay, so that is the direction. And as you move on from the charge point, then you can see that field strength is basically inversely proportional to the square of the distance. Inversely proportional to the square of the distance. As you go more and more distance, then at the infinity, the field strength will basically die down. And so there will be no field strength at the infinity, ideally. But before the infinity, you will have the field strength is as low as possible, as low that it measurable quantity. You cannot measure using certain physical devices. Okay. So this is a 3D view. So you have a 3D view of a you can say field. So here you can say that that darker area is basically indicate that you have a lower magnitude, and the lighter area basically higher magnitude. And here you have both the strength has been also be shown in terms of basically shaded area. Okay, lighter and darker area, and the direction are shown by the arrow. Okay, so the direction of the field are shown by arrow, because this is a vector field. Okay, and another type of representation of field on a particular surface. Okay, so that is called isocontour line. Okay, so that is another kind of representation. So this is one kind of representation. Basically, the strength of the field are basically indicated by color map. Okay, so this is basically called color map representation. Okay, and another way we can do this basically by combination of color map and the arrow. So this type of representation are basically, you can see that the video of I think 3 blue and 1 brown, that channel. So you can see that kind of representation. So they basically what they do, so they represent the field strength by color map and the direction by identical arrow. The arrow are identical, not varying. Okay, the length of the arrow are basically identical. So that is another way of representation. So this is basically kind of representation to understand the isocontour line. Okay, so for example, you can see that for a charge. Okay, so you have a charge field. Okay, electric you have a electric charge, and that basically creates some electric field, and surround that then the isocontour line are basically kind of surface area. So the isocontour line. So if I draw in a plane, then isocontour line are basically circle. The isocontour line are basically circle. So isocontour line means basically the line along which your field strength are identical, the equal field strength. So let's say I move from this line. So for example, let's say I move along this line. So at every point in this line having same field strength. Okay, so at every point in this line having same field strength. And similarly, if I move along this line, then you will have the same field strength as you move along this line. Okay, so if I move along this line, then let's say here, let's say for example, it is an electric field distribution. Okay, so let's say here I have 5 volt per meter electric field. So here I have 5 volt per meter. Here also I have 5 volt per meter, and so on. Okay, and for example, let's say it is 1 volt per meter. Okay, so then if you move this point, or if you move this point or this point, always you will have a 1 volt per meter field strength. Okay, so these are basically isocontour line representation. And this isocontour line representation not only done with that isocontour line, but also we basically represent the field strength using the color map also. Okay, so this type of you can say representation can easily be done using MATLAB. Okay, so we'll see some we'll provide some assignment so that you will be able to draw this type of curve. Okay, so it is not a big deal. Okay, so now it comes to Dell operator. Okay, so the Dell operator or the differential operator, it is a very important tool because you can see that the Maxwell equation are basically the curl or divergence of certain vector field. Okay, the Maxwell equation are written in terms of curl or divergence of certain vector field. So that's why it is very important to understand this Dell operator. And sometime I don't know, sometime in some book we write this as a vector notation, that in the top we write the vector notation here, and in some book we write simply nabla. Okay, and this is the universal definition of Dell operator in the Cartesian coordinate, and this definition can be obtained by similarly using the Cartesian coordinate transformation. Okay, so the same definition, this definition can be obtained by coordinate transformation method. Okay, so you can apply the same way. You can apply the same method. So what we have done for the line, okay, differential line. So what we have done for differential line, you can do the same operation here also, and you can obtain this operator in the cylindrical coordinate system. Okay, how this differential operator has been obtained. Okay, so you can do that. Okay, so it's not a big deal. Okay, then same way from the cylindrical to you can obtain the spherical one. Okay, or from the Cartesian to directly you can obtain the spherical one by coordinate transformation method. Let me zoom this one. Okay, so in the vector operation, we have seen that if we add two vectors, so that will basically leads to another vector. If we dot product two vector, then that is a scalar product. Okay, so the output is a scalar, and if you do cross product of two vectors, so that is also output is a vector quantity. And if you take the gradient of a scalar field, so please note that f is a field. Okay, so it is an operator. So del is a operator. Okay, del itself is not a you can say it is not a vector quantity. Okay, it is not a vector it is a basically operator, vector operator. Okay, please note that the del is basically the vector operator. This nabla or del is basically the vector operator. So it's operate on a field, okay, or basically function, which is a function of space, not a function of time. So if I consider that f is a function of time, and if I do this del operator, then what will happen?
Zero.
Zero. Okay, because there is no spatial variation. Okay, so there is no spatial variation, so therefore it will lead to zero. Okay, and the divergence of a vector. So if you have a vector field u, and if you take the divergence of that, so that will lead to a scalar quantity. Okay, so and that scalar quantity is also a field. So that scalar quantity, so that this f is a field, and if you take the gradient of that, so that is also a field. Okay, so that is not a basically a spatially invariant thing. Okay, so not necessarily have to be spatially invariant. So that is also a vector field. And if you take the divergence of a vector field, then that leads to a scalar field. Okay, and if you take curl of a vector field, so that is leads to another vector field. Okay, and the another operator, so that is basically called the Laplacian. Okay, so the scalar Laplacian, and you have a vector Laplacian. Two Laplacians are there. So if you do the scalar Laplacian, then the output is basically a scalar field. So if you take the scalar Laplacian on a scalar field, then the output is basically a scalar field itself. And if you take the vector Laplacian over a vector field, okay, so if you take the vector Laplacian over a vector field, so that basically leads to another vector field. So gradient of a scalar. So what does it mean by gradient? So gradient is basically indicate the change. Okay, so the gradient is basically indicate the change or basically the slope. Okay, so if let's say I'm standing, so this is let's say a kind of a you can say scalar field over a 2D surface. So if you consider this is a scalar field over a 2D surface, okay, and it is varying. Okay, and if you consider that this peak are basically low magnitude, low amplitude, and this lighter area, darker area is low amplitude, and lighter area high amplitude, then you can see that the slope will basically, so if I stand here, then the slope will point this way. Okay, and if I stand here, then slope will point this way. Okay, so basically that is basically the meaning of the gradient. Gradient is basically indicate the maximum slope in that particular point. So let's say I am standing in a particular point. So from that point, in which direction I am having a maximum or steepest, you can say gradient, or a steepest, you can say slope. Okay, so in which direction I will have a steepest slope. Okay, so because at different direction you will have different slope. So at a point, let's say you are on the valley of a mountain. Okay, so you are on the valley of a mountain, and you can see that in all the side you have mountain. Okay, so not only in a particular side, so in all the side you have a mountain, but in which direction you have a maximum slope. Okay, in which direction you have a maximum slope, so that is basically the direction of gradient, and the amount of slope is the magnitude of the gradient. Okay, so this is the thing. Okay, so okay. Here the lighter area they have represented as you can say this one. You can say low field strength, and darker area high field strength. Okay, so I think they have represented in another way. So basically, you can see that from this point, this is your slope. So it should not be this way, because in this way there is no variation. Okay, so or almost very less variation. Or this direction you are also having very less variation. Or in the opposite direction also, you can say it is a valley. It is a valley. Okay, so it is basically in the downward direction. Okay, so it will not point in this way. And also you can see that this area you can see that amplitude of the gradient. Okay, the amplitude of the gradient or the steep or the slope here is basically maximum. This area you have a maximum slope. So therefore this area, the amplitude of the gradient is maximum. Okay, so this is the basically the physical meaning or interpretation of gradient. Okay. And another thing is that basically you can say the gradient always perpendicular to isocontour line. So if I draw isocontour line for each gradient, okay, so let's say you have a isocontour line of the field, okay, the scalar field. If I draw this isocontour line of the scalar field, then we can always prove that the gradient always basically perpendicular to the isocontour line. The gradient is always perpendicular to the isocontour line. Why? Why it is perpendicular? Why not tangent? Why gradient always point perpendicular to the isocontour line? Why not tangent direction or in other direction?
Values are same in.
Yeah, because the gradient is basically 0. So if you change, so there is no change. If I move along the isocontour line, so there is no change. So therefore the gradient is 0. So in that direction, the gradient is basically 0. So therefore, in the tangential direction, there is no change. Only the change is basically perpendicular to that. So the main change is basically perpendicular to the isocontour line. Okay, so basically this isocontour line belongs to the scalar field. No, not the gradient. Okay, please note that. So this is the way you can calculate the gradient of a vector. Okay, so if you have gradient of a scalar quantity b. So you have a, let's say, volume, so some vector, some scalar quantity b, and you can find out the gradient of this is basically del v del x. So in the x direction, what is the change in the x direction, what is the change in the y direction, and what is the change in the z direction. Okay, and basically the direction is basically x. So this is in the x direction, this is in the y direction, this is in the z direction. So this is the way we basically calculate the gradient. Okay, so in the most of the cases, this is the basic definition of gradient, and this is the basically definition in the cylindrical system. Okay, and this is the definition in the spherical system. Okay, so these are basically interchangeable. You can convert this one into another one. Okay, so let's come to algebra rule for gradient. Okay, so if you do sum or difference of two scalar quantity is there. If you take the gradient and then basically this means basically sum of or the difference of their gradient itself. Okay, and if you have product, then in that case the gradient is basically gradient of the product is basically u gradient v and v gradient u. Okay, and if you have you can say divide. Okay, so if you have divide of u and v to scalar field, and if you take the divide, so this is also same as your differential rule. Okay, so v and del u. Okay, and then u del v divided by v square. And if you have v to the power n, you have a power rule, then it is basically n into v to the power n minus 1 into gradient of v. So then it comes to properties of gradient. Okay, so gradient of a scalar function is a vector function. So gradient is a vector function. Scalar function is a vector. The magnitude of del v is local maxima rate of change. So this thing I have already discussed. Okay, and del v or gradient point in the direction maximum rate of change. So as I told you that it is basically maximum rate of change. Okay, so you have in many direction you have a change, but in which direction you have a maximum change, so that direction basically indicate the direction of the gradient. And del v at any point is perpendicular to constant v surface that pass through the point. Okay, constant v surface means basically the contour. Okay, so as I told you that it is perpendicular to the contour. Okay, and then del V point towards the increasing number in V. Okay, so where V is increasing, so in that way it is basically pointing. So you can see that for example, you can say that here in the center of this surface, there is a, you can say, negative charge. Okay, so then you can say that this gradient is basically indicate the field. Okay, the electric field. So this is the direction of the electric field and the strength of the electric field. So as you go away, the strength of the electric field basically die down. Okay, and in the center you have the electric field is maximum. Or you have a you can say the flow of, let's say, certain current. Okay, so flow of current in a certain direction. So here in this direction you have you can say higher charge density, and here in this direction you have a low charge density. Okay, so if I take the gradient of this, then you can get that how the current will flow from this point to this point. Okay. Okay, the divergence and the curl I will discuss in the next class. So tomorrow is holiday or regular class will be there? Do you know? Is there any holiday tomorrow?
Yes, sir. Tomorrow is a holiday.
Yes, sir.
Oh, it is holiday. Okay. Okay, then I'll continue next Monday. Okay, no, not Monday. We don't have class in Monday. Wednesday. Okay. Okay, so goodbye for now, and see you in the next class. And in the next class, we'll discuss about the divergence and curl, and then we'll move into Maxwell equation. Okay, so. So do you have any question or query?
No, sir, just upload the slides.
Okay. So you can download this the today's slide from Professor Ram's website, because so that so you can go to here. So let me open this team. Vector class material, introduction.
Yes, sir. Previous slides are already uploaded. I was telling about today's class slide.
Yeah, today's class slide you can download from there here itself. Okay.
Okay,
so
sir.
Actually, I have used this one. Why it is not opening? I think due to online mode. No? Okay. So you can click there and you can go to the directly that course website. So there you can download. Okay. So this course website you can directly download from here. That review of calculus. I think I was discussing differential length. Okay. So this one, and then integration, and then Dell operator. Okay. So this slide and this slide, these three. Okay.
Okay, sir.
Okay.
Thank you, sir.
Okay. You're welcome.